Okay, now that we have talked about the 4 different causes of mutations in DNA, I'd like to talk to you about some of the repair mechanisms. And this is not in any way a complete list of how things get repaired, but it's a good start, and it's some of the interesting things that I see from the book. First of all, I want to talk about alkylation. Remember, we said that you can end up with a methyl group added on to a guanine, and in this case we have a guanine and a cytosine here, and if we get that guanine methylated, then all of a sudden you have a mismatch here, and this doesn't pair very well anymore. That can actually be detected by repair enzymes, and this is a process, as noted in your book, that's called direct repair. There is an enzyme, and it's called O6-methyl G transferase. And your book goes through this in some detail, but let me show you what is going to happen. Here is the enzyme right here. I'll do that in green because I often use green for enzymes. And this is an enzyme active site, and it has a cysteine in the active site. And what we also have, as we almost always do in enzyme mechanisms, is a base. And that base is going to activate the cysteine, as it always does, by deprotonating it. And that'll make the thiol into a thiolate, negative charged, and a really good nucleophile. And this enzyme recognizes these methyl guanines, and it brings them close to that cysteine, and you have a direct attack on that alkyl group. This methyl oxygen bond is going to break, and it's going to collapse back to a carbonyl, and we're going to go and pick up a proton, maybe from a water or from a general acid. And at that point, we end up with a reestablished good G and C together, and we have the proper base pair. What's interesting about this is that we end up with the cysteine having a methyl group on it, and I think this is one of the reasons I like to talk about this, is because that methyl group never comes off that cysteine. So I've been kind of fibbing here a little bit. This enzyme is actually not an enzyme, and that's because it's not catalytic. It can do the job, but this is a dead end. And once you make that protein and it does its job, it's of no use anymore. It has to be degraded back to amino acids. So a very curious example of how a particular enzyme does a job but is not actually catalytic and therefore not really an enzyme. Okay, let's move on to a separate situation. Let's go on and talk about base excision repair. This is a great use. For example, this might be useful for spontaneous conversion of cytosine to uracil. And we end up with a U present. Now, here's an interesting little side note, by the way. Let's say this U right here came from a C that spontaneously went through hydrolysis and converted to a U. Now, if we had uracil in DNA, we wouldn't know if this was the correct base or if this was the correct base, and we wouldn't know which way to fix it. But because we have thymine instead of uracil in DNA, we know that this uracil cannot be correct. In fact, that's why people think that there is uracil and thymine different between RNA and DNA. It's because the spontaneous C to U transition shows up so often, we know to fix it. And the way we do that is you create a hole right there. You excise out that uracil right from the backbone, and you actually create, through base excision repair, a apurinic hole. We talked about that earlier. And once you have an apurinic hole, we'll fix that on the next page through nucleotide excision repair. So more on that in just a minute. But how do we get rid of the U itself? It's a really fascinating enzyme, and I love to talk about it. It's in the book, but I've also made a crystal structure of this protein. It's called uracil DNA glycosylase. It's a very famous enzyme, and they actually have a crystal structure of the protein, which is shown here in green, attached to DNA, and that DNA has a uracil in it. So they got a beautiful crystal structure for this. And here's the whole crystal structure, but I decided to take it apart so you could see what's going on. In fact, we can see over here on the right that this is the DNA, and the uracil normally would be down in here, as you'd expect, trying to base pair with the other strand. But this uracil DNA glycosylase scans along the DNA, and when it finds a uracil, it flips it out from here out into the active site of the enzyme, which of course I'm talking about over here. It's now, you can see the uracil base right here, buried in that active site. So it wrenches that bad uracil base out of the DNA into the active site and then chops it off with a water. And of course, what I mean by that is it's gonna chop it off right there and release that base. And now we have a backbone without a base, as I said above, an apurinic hole. Okay, that's kind of a cool enzyme. Let's move on to the very last part, and that's nucleotide excision repair. All organisms have the ability to do major repairs through this process. And this process is in particular for fixing the apurinic holes we just talked about, and also for thymine dimers. These are problems that happen on one side of the DNA only. So for instance, let's say we have a thymine dimer here. And like I told you earlier, a thymine dimer is going to cause a distortion of the DNA backbone. Now, like I just said a minute ago, we've got a distortion here, but the other side is fine. And we can use that to repair the other strand because we know how to base pair with that. So we have a couple of steps we do, and first we're going to cut the DNA backbone on either side of the offending area. That's going to be a nuclease activity. That's what a nuclease is, to break phosphodiester bonds. So that cut's going to happen right here and right here on either side of the thymine dimer. That's going to then be chewed out by a nuclease. A nuclease removes the so-called bad DNA with a thymine dimer. And at that point, we then come in with the repair. And the repair is going to happen with a DNA polymerase 1. We've talked about the action of DNA polymerase, and DNA polymerase 1 comes in. It uses DNTPs. Remember, we got to have monomers to synthesize into a polymer. And lastly, the ligase enzyme seals it up. So this new blue area we have right here is going to be fresh. It's going to be correct because it's copied from the other strand, and it gets sealed up by that ligase. And this is how we do it, and this is how bacteria do it. And if you have problems with this, by the way, you can actually have genetic defects or mutations in it. Defects in this, in humans, defects in this repair system can lead to a couple of diseases. One of them is called xeroderma pigmentosum, and that's something that causes massive skin lesions and pigment problems and scaling skin, and it can also cause cancer because if you can't repair DNA from thymine dimers, you're going to have massive early cancer, because that's how we avoid cancer, is to repair mutations that would be problematic. Okay, that's the end of our mutation repair section, and we'll leave it at that.